Alright, so in this video I'm gonna be explaining another important paper with the title Long Range Graph Benchmark. This paper in NeurIPS 2022. Graph neural networks that are based on the message passing paradigm generally exchange information between one-hop neighbors to build node representations at each layer. In principle, such networks are not able to capture long-range interactions that may be desired or necessary for learning a given task on graphs. Recently, there has been an increasing interest in development of transformer-based methods for graphs that can consider full node connectivity beyond the original sparse structure, thus enabling the modeling of LRI. However, MPGNNs that simply rely on one-hop message passing often fare better in several existing graph benchmarks when combined with positional feature representations, among other innovations, hence limiting the perceived utility and ranking of transformer-like architectures. Here we present the long-range graph benchmark with 5 graph layering datasets. This is a molecule with LRI, dotted lines showing 3D atomic contact that are not trivially captured by the graph structure. So we proceed to study the key characteristics that can help to determine how a graph dataset could be appropriate to gauge whether a GNN can or cannot model long-range interactions. For example, graph size is very important, or nature of the task. For example, nature of task can be understood by directly related to the problem's range of interactions. The task can be either short range, that requires information exchange among nodes in local or near local neighborhoods, or long range, where interactions are required far away from near local neighborhood. For example, in zinc molecular dataset is associated with counting local structures, and it has been revealed that a substructure counting based model would optimally require count of 7 length substructures for the best performance. So if the graph size is considerably large, it may not warrant that models with long-range signal propagation are best suited unless the nature of task determines so. Also, contribution of global graph structure to task. That message passing graph neural networks rely on information aggregated from local neighborhood. So the global thing, that's why you need positioning, encoding, and many other techniques. So this is a node classification dataset, Pascal, and you see the visualization of a sample image. It's regions and rag boundary graph from that dataset. Similar to that Pascal, COCO SP is a node classification dataset. So these are the datasets. For example, PCQM, molecular property prediction, is one of the most important popular transform benchmark. And you see the statistics of different benchmarks. Also peptides, molecular graphs is very important. Peptide function, peptide struct. And they compare, for example, graph convolution with different models for these datasets, peptide func and peptide struct. Of course, there are correlations of labels in peptide function and peptide struct that you can see here. We visualize it using Pearson correlation between the classes. So there are 3 principal lengths, for example, in this kind of data set. Or this is large size visualization, This is a peptide sequence. GLLGP, this is a peptide sequence. And you see different lengths, 1, 2, 3, different length. As you saw here, different principal length of that. And so these are the data sets, Pascal, that I explained, are very important to understand long-range interactions and the problems of graph neural network.